Completely different types of.
Yeah, it makes sense. Kind of like this method.
Yeah. Yeah. Sure.
It's like enjoying you know,
There, I mean,
which I
So
feel
you apply for the team master.
basically targets and which I feel
Beginning, I thought I was not qualified. Mathematics is the real life. It's the real life. Because I think the evil is kind of like
Alright, so before we start, a couple of announcements. I was supposed to put up Hobart Bay yesterday, but I was a little sick, so I didn't end up doing so. So it will be out today. It will be a little shorter than the first two homeworks, and it will be due the Friday after fall break. Okay. So that's homework 3. Okay, and so the other more important announcement is about the project topics. Okay, so today I will also list out a bunch of project topics. Okay, so this will be about 20 papers, and I expect not more than three groups per paper. And I will describe what the project entails and so on. So I would like to have not more than 3 groups per paper. So watch out for these project topics and please claim them, as soon as they show up. Okay? And form groups of 2 to 3 people. You are welcome to do it by yourself, but I would recommend doing it with others because you'll all be judged at the same level. So it helps to have 2 or 3 people. So I would suggest groups of 3 because that way you can cover a lot of, you won't have too many groups per paper and we can cover most of the papers that will So that's about the project. And as I said, what it involves is you will have a research paper, and this will be an implementation project, firstly. Okay, so there's some exceptions. If you want to do something else, talk to me. Okay. So it will be an implementation thing. You will start off with a research paper, which will presumably be on it will present an interesting algorithm for some problem. Okay. So what you will do is either try to implement some aspect of it, or try to implement some heuristic based on this research paper. Okay. So sometimes the algorithms in the paper themselves could be complicated. Okay, so in that case, you won't try to basically mimic what they are doing. You will try to read the paper, understand it, get essentially the algorithmic idea there, and try to see if you can come up with some heuristic for the same problem. Okay, and you will try it on some data sets. Okay, and the goal of this project is that you you implement some of the things, some new algorithm of your own on a new data set. Okay, so that's kind of the goal of the project. Okay, any thoughts on that? Any questions? Okay, so I'll also send the sample report from previous years. I'll put it up on the Canvas page. This should give you a sense of how to do it. Was there a question? Alright, so the plan for today is we'll continue the topic of flows. We'll see a couple of applications of flows. And I switched around the topics a little bit. I wanted to do linear programming. Then I realized that if I did probabilistic algorithms, then I can do some more interesting stuff in linear programming. So I thought I would do randomized algorithms first. Okay, so today we'll start off with that topic, and it's also better than linear programming in the sense that there's a break next week, and if if I start linear programming now, and if you forget everything, I'll break it. I'll have to start all over. So I think with randomized algorithms, it's easier because it's just some simple examples. Okay. All right. So that's the plan for today. Okay. So let's start by recalling what we saw last week. Okay. So we saw two problems and we saw connections between them. Right. So one is the max flow problem, where you're given a directed graph. You had a source and a sink. Every edge had some capacity, which is the amount of flow that could flow through it. Okay? And you wanted to route as much flow as possible without violating any of these edge capacities. So that was max flow. Min cut was again also a problem on directed graphs. Now you wanted to remove as few edges as possible so that in the graph that remains, there is no path from S to T. And both were problems on directed graphs. And so what we saw is that the maximum flow you can send from S to T is always upper bounded by the min cut. Okay, so between S and T. Okay, and this is intuitively easy because you can imagine removing all the edges in the cut. Now there is no more flow, and then sometimes so now there's no way you can send any more flow. Okay, and the most flow that could have been on these guys is the sum of edges. Okay, so that's we saw a more formal proof of this last time. Okay, so I'm not going to spend too much time on that. Okay, so but more interestingly, what we said is that this inequality is a nice way to certify the optimality of a flow algorithm. Okay. What we said is that suppose a flow algorithm produces some flow, and I want to certify that this is the maximum flow. All I've got to do is come up with a cut whose value is equal to the size of this flow. And the inequality, the first inequality there says that this flow is bound to be the maximum flow. Okay. Because because there exists a cut that equals to this value. Okay. So that's so this is a good way to certify optimality. In fact, for the algorithm we saw last time, we gave such a proof. Okay, so this is what we did last time. So we gave an algorithm for max flow, and we showed the optimality of this algorithm by demonstrating a cut whose value is equal to the value. And we did this for any graph. Okay, and in the process, therefore, we've proved the following theorem that in every graph, the value of the max flow is actually equal to the value of the min. Okay, so this is what we saw last time. So the details are not terribly important, but this kind of view about flows and cuts is what you should remember. Okay, that the value of the flow and the cut are related to one another, and in fact they're always equal. And a cut always gives a clean way to certify the optimality of the flow. So these are things you should remember. Okay, and this algorithm itself, it involved constructing what was known as a residual graph, and it involved finding what are called augmenting paths on this residual graph. Okay, so you always kept some flow f, and then you built this residual graph based on this flow f, which we call G sub f, and you always find an augmenting path in G sub f. You add that path to your solution and keep going. Okay. And we kind of interpreted it also as sometimes if you don't build this residual and you just remove the capacity, then you can get stuck in local optimum. Okay, and we said that this residual allows you to repair some flows in a clean way. Okay, so this is what we saw with examples last time. Okay, and this algorithm is called the Ford-Fulkerson algorithm, and this is very old. This is probably Alright, so what's the bottom line? So we can solve the max flow and the min cut problems in polynomial time. And there's also a clean connection between them. And what we saw is just one algorithm for max flow. This is still an active area of research, particularly for directed graphs. We don't still understand what is the best possible algorithm for flow. Yeah, so interestingly, for cut, the situation is better than it is for flows. Okay, so even though these two are equal, it's not always the best algorithms for one don't always translate to very good algorithms for the other. Alright, so today I want to talk a little bit about applications of this. So the first application, so these are, you'll see more of these applications in the homeworks, but yeah, so the first application is a very simple one. Okay, so suppose I give you a directed graph, and it's unweighted. Okay, so there's no weights on it or anything, and I give you. Sorry, I should have written edge disjoint path. Vertex disjoint paths we'll see in the homework, but yeah, I want to talk about edge disjoint path. So what is the question? You are given a directed graph. So there is some G, and you are given U and E. And you want to find a bunch of edge disjoint paths from U to B. Okay, so they can share vertices. This is one path. The second path. So these paths don't share any edge. And I want you to find as many as possible. So what would be a natural way of doing this now that you know about flows?
It seems like, well, if you do the min, or I guess, but if you do the min cut problem, then the maximum number of paths can't be more than the number of edges that you remove. Since, like every, yeah, otherwise it wouldn't be a cut.
Sure, but I want you to find paths, right? Mm-hmm. So something easier than that. Yeah?
So you find the flow and then find the path of the flow, then remove all those edges and start again.
Well, you don't have to remove, you could do that. So what he's suggesting is find the flow and you remove all those edges, but you run into the same kind of problems that I described last time, right? So you're just saying find some path, remove it, find another path and so on, right? But we already saw that this can get stuck in local. Okay? But what if we know how to get rid of it. So let's say you just run a flow algorithm. And was that what you were saying?
You could make U and V the source and the sink.
Yeah, so just make U and V the source and the sink. Have a capacity of every edge to be 1. So capacity of every edge equal to 1. The effect this has is that no two flow paths can go through the same edge. Right? Because this would give, if you solve this problem, you would get different flow paths from U to B. No two flow paths can go through the same edge. And this is why you get edge disjoint paths. Okay. So all capacities are equal to 1. Okay, so now you should ask me, okay, why would the max flow be integral, right? So you could have a value of half on one flow, half on the other flow, and then they could share edges. But that doesn't happen because if you see how our algorithm for flow runs, and if you assume that all the edge weights were integers, then it will never route a fraction. Okay, so this is a basic property of flows, that if all the edge weights are integral, then your maximum flow will never route fractional flows along lines. Okay, so if you use that observation along with just setting every capacity to be equal to 1, you get multiple edge disjoint paths from U2. So yeah, in your homework you will see how to get multiple vertex disjoint paths. Okay, but any question on edge disjoint paths? This is the most basic application of flow, so you should understand this. Okay, so it's just simply you declare U and V as the source and the sink, and you try to find the maximum flow. Okay, and these flow paths have to be edge disjoint because the capacity of every edge is small. Alright, so this other problem, the second problem, which is also very simple, is what is called edge connectivity. Okay, so here you are given an undirected graph. Okay, and you want to remove as few edges as possible so that the graph gets disconnected. The only difference between this problem and the previous stuff I've told you is that firstly it's an undirected graph, and secondly I'm not specifying which vertices must be cut. All I'm saying is that the graph must be divided into two non-empty disconnected pieces. Okay. So I don't want any piece to be empty, and this is how I do. So how would you do this problem if you knew how to solve it?
Isn't this just the same as the min cut problem? Just you set the weights to 1, and then you just have to check each pair of vertices, which is like n squared has an n squared term in there, but it's still polynomial.
Yeah, so what he said is exactly right. So what he said is, I mean, it's no big deal if you don't know which vertices to cut, because if you don't know the S and T, that is because you can just try all of. And this is one solution. You can do a little bit faster than this. I mean, actually, you can do much faster than this, but this is one valid solution. Okay, so try all possible S and T and try to see if there's a cut. And you might say, okay, well, we saw only for undirected graphs, but how do you convert an undirected graph into what we saw?
You can just take each edge and make 2 directed edges, like one that goes one way, one that goes the other way. So it doubles the number of edges, but it preserves the same sort of sets of paths.
Yeah, so you can replace every edge, every undirected edge with 2 edges. One going this way and another going this way. And this would, and if you've disconnected S from T, then you have to remove both edges. So this is how you convert an undirected graph into a directed. Okay, so this is edge connectivity. This is the general idea. Okay, so these are some very trivial examples. There's another natural example that people often study, and this shows up in image segmentation. So often you have an image, and you can view an image as a graph where the edge weight. So you can imagine the vertices are these pixels, and the edge weight between these things. Maybe you also have these diagonals. This doesn't matter, is the similarity between these 2 pixels. Okay? So edge weight represents similarity. And now maybe you know that a few of these pixels, maybe these guys, are the foreground. And maybe you know that some of these people are background. Okay? And you want a small cut that separates the foreground pixels from the background pixels. Okay. Because a small cut in this case means that you're cutting edges. Edges correspond to neighboring pixels that are not very small. So that's the intuition here. And this is a popular problem. The only difference between this problem and what we saw earlier is that now you have sets of vertices. Right? So you want to say that I want to separate this set S from the foreground set from the background set. Right? It's not like two different vertices that you want to separate. You now want to cut sets of vertices. Okay. So is this problem clear? So we have two sets. So let's call this S, and the background vertices I call them. Okay, so these kind of algorithms are often used, some of the oldest algorithms for image segmentation. Okay, so there's much better ways, but this is one way. So, basically, this should be a tab. So you see in your homework how to do this problem. Okay, so the only difference here is that you don't have one S and one T. You have a set of vertices. So, alright, so this is one application. And this final application is actually related to what we've seen. So it is. So remember the matching problem that we studied a bunch of times in the class. This would be my favorite example. So you have a bipartite graph, and you want to assign. You've got some edge weights, and you have n vertices on the left and n vertices on the right. And you want to assign these gifts that we call these children, and these gifts. And you want to assign gifts to children so that the total happiness is maximized. Okay. And now imagine a binary version of this problem, okay, where every happiness value is either 0 or 1. Okay, so a child is either happy or is not. Right? So and our goal is now to make as many children as possible happy. So this is so this problem is called this is called the maximum matching problem, and so I want to say that this can be viewed as a flow problem. Okay, so it's slightly non-trivial. So the claim is flow. Okay, as a max flow. Yeah.
I think connect these bits on the side to the source node. And others on the right side.
Right. So what he's saying is how you reduce this problem to a max flow problem. Okay. And actually, my picture kind of started giving out the hint, right? So the idea is to add an extra node on the left, which we call the source node, and an extra node on the right, which we call the sink. Okay. And okay, so firstly, we also direct all the edges to the right. Okay. So let's say I put edges only when the happiness value is 1. Okay, so and if the happiness value is 0, I'll just ignore the edge because that's an edge with capacity 0. Okay, so I'll just not put that edge. Okay, so suppose I have this sort of a network. now what he suggested is adding edges from the source to every vertex on the left and adding edges from the sink to stuff on the right, to the gifts. Okay. So remember what we are doing, right? So we had an instance of this gifts and children problem, okay, where the happiness values were binary, 0 or 1. Okay. And this was an undirected graph where you had undirected bipartite graph. We made it directed by putting edges going to the right. And we are also adding a source in the sink. And we are adding edges like this. Okay, so we are adding n edges on the left and n edges on the right. To make it, and I'm making the capacities of all of these things 1, of all the edges 1. Let's say I make the capacities of these guys also 1. So the claim is that the flow in this network has something to do with the maximum number of children who get gifts that they are happy. Okay. Why is that? Actually, a somewhat simple operation, but it's you should try to understand. Yeah.
Since we have only one edge from the source to every child, the maximum happiness that we have is 1. It's being happy.
Yeah.
And so then if we maximize those edges which get used, so that most children are happy, that would be our maximum solution.
Okay, so what he's observing is that, so I guess there's a bunch of very simple observations you should make. Okay, so the first one is, any flow path must have exactly 3 edges. Right, so it must go to a child, must go to a gift, must go to the sink. Okay. And the reason is that there's no backward edges or anything, right? So there's nothing more complicated that could go on. Okay, so every path just has 3 edges. This is the observation 0. Okay, so is every flow path has 3 edges. And the second thing is what he said, right? Like through every child, there can be at most 1 flow path, because there's a capacity of 1 that goes into that child. Okay, so every child, and you can use the same reasoning for the gift as well. And gift is only involved. In at most 1 flow path. And these two observations essentially let you go from a flow to an assignment, right? Because you look at the maximum flow, okay, and each flow path is essentially, it has 3 edges, so it contains 1 child and 1 gift. Okay, so you assign that child to that particular gift. Okay, and that's it. So this is a valid assignment because no gift will be assigned to 2 children, because you can't have flow paths that look like this. Right? So you can't have flow paths that, let's say, go to the same gift to the same. Because in this case, this edge has capacity only 1. Okay, so none of them. So you can't have a flow path like this. Right. So this is a very simple reduction, and it shows that at least when all these happiness values are binary, then the optimal solution can be found by just looking at the maximum flow. So it turns out if these happiness values are not binary, you can't do stuff like this, because some of the happiness values can be much larger, and then you don't know what capacity to put on the left edges, or on the right edges. Okay, so that becomes a problem. So that's a simple exercise for you. So figure out what goes wrong. these are the happiness values, are non-binary. Okay. And yeah, so one thing maybe I'll mention here because we'll see it in a little while is that the problem of finding out if every gift can be if every child can be assigned a gift in this binary setting, it's called the perfect matching problem. Okay, so that's like asking is the max flow equal to n? Because can every child be given a gift that he's happy with? So that's called the perfect matching problem, and it shows up in a bunch of applications. Alright, so these are some applications. I thought that I'd mention another popular example. So this is called baseball elimination. I don't know if people are familiar with this. I certainly wasn't until I read about flows. But so basically, you have teams that play against one another, and let's say you look at this table, right? So every team plays against a bunch of other teams, and so this table shows two things. So this middle part of the table shows essentially how many wins people had, how many losses each team had, and how many left to play. And on the right is a matrix that shows that for these teams, it shows the number of games left between these two teams. Okay. So what is the number 5 here means that between New York and Baltimore, there's 5 games left. Okay, or between Boston and New York, there would be 7 games left, and so forth. So is that? So is this picture clear? Okay, so it's showing two things. One is the obvious standings table that you will see, and the other is just the games left to play against one. And now you could ask, okay, so, and in this case I haven't written how many wins and losses Detroit had, but let's say I told you that Detroit had only 46 wins so far. And you could ask, will they be eliminated in the sense that does it have a possibility of finishing top of the table? In this case, it's trivial that you cannot have because if it's only 46 and you have only 28 games left to play, then the maximum number of wins you could have is only 74, which is already less than whatever New York had won. Okay, so there's no way Detroit could jump to the top of the table. Okay, so in some sense, it's eliminated from being the winner. But so this is a trivial scenario. Right? But you can ask, okay, what if W5 is 47? Okay, so can they still tie with the top? Right? So in this case, 47 plus 28, which is the number of games left for them to play. You might end up being 75. But could that happen? Yeah, what do you guys think? In this scenario? So suppose Detroit wins all the remaining games. Could it end up at the top of the table? Or could it tie?
So with the games against each other, does that mean that they have 3 games and 4 games? So 3 against New York and 4 against BA.
Yeah.
And so there wouldn't be, even though there's 28, I just don't understand how the 28 comes to the other numbers.
Oh, this is only with these guys, right? So I'm assuming there's other teams that I haven't listed. Yeah, I'm sorry. Yeah.
Okay.
Yeah.
So I think Baltimore has, I think it's not possible because Baltimore still had 5 games against New York. New York needs to lose all the games from their own. So Baltimore will have
76, right? So yeah, so that's perfect. So what he's observing is that in this scenario, I said that New York and Baltimore have 5 games against one another. Okay. Now, if New York won even one of those games, it would become 76. It would have 76 wins, and therefore Detroit cannot be joined first. Okay. So otherwise, Baltimore will have to win all of these 5 games, and this would then have 76. So in general, you can see that there's some non-trivial, if you have a lot of teams, deciding whether a team is eliminated at this point or not can be a tricky thing. Okay? And it turns out this can be formulated as a clean flow problem. Okay, so I'm not going to show that to you, but I'm going to give a link on the course page. Okay, so this is if you're interested. Okay, so this is just one. You wouldn't suspect that something like this can be written as a flow problem. Okay, not a priori, not if you didn't know about flow. Okay, so yeah, so that's so that's the set. Okay. All right. So these are I guess the examples I had about flows and cuts. There's a lot more. And some of these examples you'll work out in more detail in your homework. And yeah, so with this I wanted to conclude flows, and I want to move on to randomness. So this is what we'll talk about for the rest of today and next, actually almost a couple of weeks from now. So, all right. So what is, so this is one aspect of computation that you don't see in like very elementary classes, but it's one of the most basic aspects of computation. And the motivating question here is, does allowing randomness in designing algorithms lead to faster algorithms? Okay, so it's a very, very simple question. And you might expect, why would making some choices randomly help? Right? So that's one of the first things. So let's start with a very toy example. Okay, so the example is the following. Okay, so you're given an array of n numbers, which are denoted by a1 through an. And I promise you that n by 2 of those elements are 0. Okay? And your goal is, of course, to find one index I such that a of I equals 0. Okay, so it's the question here. So yeah, so somebody promised you that half of these elements are 0. And now, if you think of an obvious answer to this, which is you just go through the array and see which one is 0, this could take time n by 2, right? Because maybe all the zeros are like from n by 2 onwards. So yeah, so you could ask, is there a better way of doing it, right? Without examining essentially n by 2 of these. Okay, so now that we have randomized elements, what would you do? What is a simple strategy to try to find an index that's 0? So suppose you had to solve this problem. What would be a better way that would be much faster than n by 2? Right? Yeah, so you just randomly pick an index and check if a of I is 0. Okay. If it fails, okay, you got unlucky, and you try another one at random. Okay. You keep doing this until you succeed. So very, very basic problem. So while that's a lot. You just pick random one. And check if a of I. And if you find one, you just start. Now, of course, this is an algorithm that could, in principle, never end. right? Because you could always be unlucky somehow. But what is the probability? When you could ask yourself, what is the probability that it fails for, let's say, t steps? Yeah.
So this is like similar to the exchange problem. Like if we have half probability to get an element that is 0.
Mhm.
If they say how many tries do we need to get at least one time?
Yeah, so this is essentially like asking if you had a coin that succeeds with probability at least half. Okay, so how many times do you have to toss it to see one head? So that's essentially what you're asking. And you can argue, okay, so what is the probability that it fails? So since all these tests were just totally independent, so the probability of each of these guys failing is less than or equal to a half, right? So the probability of failing in every step, in each step, is less than or equal to half. And the probability that you fail in all of them, all the steps, is therefore less than or equal to 1 by 2 to the t. And that's because each step, because the steps are all independent. Okay, so that's why you can multiply it. And this is what you have. Okay, and if t is, let's say, 20, then your probability of failure is much less than 1 in a million. Yeah.
When you say random, does that mean the same number gets chosen twice?
Yes, in principle, yes, but it's unlikely because you are picking a random number in the interval 1 through n. So, yeah. So actually, that's if you know about it, you have to pick around square root n numbers to find two things that match. Because, otherwise, you will all of them be. Yeah, but yes, in principle, you might pick the same guy if you are on that. All right. So that's so this is the argument. Okay, so in each step, the failure probability is less than half, and overall it's less than 1 by 2 to the t. So if t is about 20, then you have 1 in a million chance of failure. Okay, and these are good odds for most people. Yeah.
Why do you say that it's going to be less than?
Oh, because so I have only promised you that n by 2 are 0. There could be more that are also 0. Right? So yeah, so that's why it's less. But if exactly n by 2 are 0, then it's exactly. Yeah. All right. So this is a toy example. Now you could argue, okay, this was tailor-made, right? So this is a very simple example in which things fail. But it turns out there's non-trivial examples of this. So let me give you an application. So this is called. This looks much more non-trivial than what I wrote. Okay, so let's consider two polynomials. Okay, so these are polynomials. These as so far it's just one variable, but it could in principle be multivariate polynomials as well. Okay, you've got two polynomials, and I ask you, are these two polynomials identically equal? Okay. And in general, you would think of, I actually couldn't find very good examples of polynomials. These two, I think, are equal, but couldn't find good examples of multivariate polynomials that are identically equal, that don't obviously look identical. So, yeah, alright, but yeah, so in principle, there could be n variables, degree d. Okay. Now, if you did not know anything, right? So, if you didn't think of the notion of randomization, right? So, if somebody gave you two n-variate polynomials in degree t, and each of them has an expression where p of x is easy to evaluate. Okay, for a given x, it's easy to evaluate. So, if they gave you polynomials written in this form, the obvious way of checking if these two are equal is to expand out all the coefficients and check whether all these coefficients are equal. Right? This is like in this case, you may want to expand out the first polynomial and check if every coefficient matches the corresponding coefficient below. Okay. This is clear. So this would be the natural algorithm for this problem. But now, and if you had an n variable polynomial of degree d, you can see that the number of coefficients can be something like n choose d. Okay, because you can have a ton of coefficients, right? And this can quickly become exponential. I'll show you an example in a little bit. Okay, so this can cause problems. So now, but it turns out that there is a very simple algorithm. So say we pick a random x and check in some interval. Okay, so let's say we pick a random integer in the interval 1 to 20 or something. And check if p of x equals q. Now this can be done significantly faster than actually computing this polynomial, computing all the coefficients. Because you just plug in this value, let's say I decided to plug in x equals 20, 19 or something, then I just have to multiply these numbers to evaluate p, and I have to compute something to evaluate q. Okay, so this is typically much faster than actually finding all the coefficients. Now, so it turns out that there is a very interesting dilemma. So now what you should ask is, what is the probability that these two were not equal, but still p of x was equal to q? Does that make sense? That is your failure probability of this test, right? And when would that happen? So when could it be that p of x is not equal to q of x? P of x not equal to q of x as polynomial, but p of 19 equal to q of x. Yeah.
When those curves intersect on the graph at that point.
Yeah, so geometrically this happens if somehow 19, at the point x equals 19, these two graphs pass to the same point, right? And more formally, so this is like saying, if I look at the polynomial r of x that is defined as p of x minus q of x, then 19 is a root of this polynomial. So this is the only place in which, this is the only situation in which this could happen. But now you can see where this is going, right? So p of x minus q of x, each of these was a degree 5 polynomial. So p minus q is also a degree at most 5, and it has at most 5 roots. Okay? So unless you happen to be very unlucky and you hit those 5 points, you're bound to find a point where p of x is not equal to q. So if I just searched in a range of like 30 different values, then this would be fine. Okay, so for single-variate polynomials, this is actually a deterministic test, right? Like you could actually literally do this for 6 different points, and if all of them were equal, then you would conclude that p is equal to q. But for multivariate polynomials, you could have exponentially many zeros. But still, it turns out that this test, you can prove that it succeeds with very high probability. Okay, so this is what is called the Schwartz-Zippel lemma. I will not mention, I'll not go into the details. But this is a very, there's a very powerful way of testing if two polynomials are identically equal. Okay, and this is called identity testing, because in some sense you're trying to test if some polynomial, this r of x is equal to 0. So here the idea is generally that you can evaluate these polynomials quickly, but expanding them out is cumbersome. So this is called the Schwartz. Oh, this is
Yeah, people like different spelling.
I think Schwartz is fine. So, all right. So this is one setting. So where does this arise, right? So where do you have polynomials that you can evaluate easily, but you can't expand out easily? Okay, so I wanted to give one application given that we just saw this problem. Okay, so this is, let's look at this perfect matching problem. Okay, so what is the perfect matching problem? So I gave you a bipartite graph. This is going back to happiness children's version. Right? So you have n words, and things here and things here. Okay. And you have some edges, and you want to know if if every child can be paired up with a gift that he's happy with. So this is a binary version of the problem. Okay, so I just defined this perfect matching problem. So it's you're given this bipartite graph. You want to know if every vertex, if the vertices can be paired up using it. Okay, so why is this problem related to polynomial identity testing? So it turns out that suppose I introduce a variable. Okay, so introduce variable xij for edge ij. Okay, so if there is an edge between the ith vertex here and the jth, ith child and the jth gift, that means that the happiness value here is 1. It's not 0. There's no edge means that the happiness value is 0. So introduce a new variable of this kind. Now let's construct this matrix. This is an n by n matrix where I put a 0. It has zeros on the diagonal. No, it could have anything on the diagonal. Yeah, so I put a variable value of xij here if ij is an edge and 0 otherwise. So ijth entry of this matrix equals xij if ij is an edge and 0 otherwise. Okay, so note that x's are variables, right? So this is like x, y, z kind of things, right? So I just have multiple variables. And this matrix I will call M. Now, what is the determinant of M? So is my question clear? So actually, let's draw a very simple example for which what I'm saying is actually easy, but the notation may be cumbersome. So let's say I have this graph. I have three children and 3 gifts, and I have only 4 edges. I'm introducing one variable per edge. So just out of convenience, I will call it x, y, z, w. Yeah.
So is there a solution for the happiness problem, or is just a
No, it's the instance of the happiness problem. So it's a bipartite graph where when I put an edge, if that happiness value is 1, I don't put an edge if it's 0. Okay, so it's an instance of this binary happiness problem. Okay. Yeah, well, that's a good question. Okay, so I'm just defining some instance of the happiness problem In fact, I should have, in principle, I should have had other edges and had weights of 0 on those. Okay, so I'm just drawing the, yeah, since this is the binary version, I'm only drawing the edges that we want. Okay. So in this case, is there a perfect matching? Yes, and what is the perfect matching? It is, yeah, so it is X, W, and Z. So 1 gets matched to 1, 2 gets matched to 3, 3 gets matched to 2. So this is 1. And so in this case, the matrix I am constructing is a 3 by 3 matrix where 1, 1 I have X, 1, 2 I have Y, 1, 3 is 0, 2, 1 is 0, 2, 2 is 0, 2, 3 is W, 3, 1, 0, 3, 2 is Z, 3, 3 is So how do you compute the determinant of this matrix? If X, so this is the matrix I'm constructing. And this M that I wrote down is just a more general version of the same thing. So, right, so how do you write the determinant of a matrix? Just out of curiosity. So what formulas do you guys know for determinants? I'm sure at least some of you know this thing where you like cross out rows, columns, and stuff like that, right? But sorry. Yeah, so I don't know if you guys know this formula that if you have the determinant of some matrix M, what you can do is you can do a summation over all permutations P, okay, where a permutation of numbers from 1 through n. Okay, so P is a permutation of numbers 1 through n of so M1 P of 1, M2 P of 2, so on up to n P of n. This is an n by n matrix times a sign term that depends on the permutation. Okay, so I will call it the sign of P. So this is I now forget what formula this is called, but this is a very well-known formula for the for the determinant of a matrix. Okay, so it's a product over sum over all permutations of a sign term, which is defined as the sign of the permutation, times I pick the pi entry in the ith row of the matrix. Okay, so this is like so if my permutation happened to be 1, 3, 2. Then I am picking the first element here, the third element here, the second element. Okay, so that's what this is. And if my permutation happened to be 3, 1, 2, then I would be picking this guy 1 and 2. Okay, and I'm taking the product of those terms. And I'm adding them all up with some sign. Okay. So if you don't have a sign, it's called the permanent of this matrix. Okay, and that's related to, that has some complexity implications and so on. Okay, so but a determinant has these signs. And actually the very interesting thing is that if you didn't have the signs, this quantity is NP hard to compute. It's sharp hard to compute. But if you had the signs, then you can compute this in polynomial time. Okay, so a determinant, as you guys know, can always be computed in polynomial time. Okay, even though this expression makes it look like it is a sum over all permutations, right? So it has n factorial terms. But there are other ways of computing determinants, which also you guys have seen, right? This is that way where you like cross out those parts. That's fast execution. Okay, and yeah, there are also Gaussian elimination. Okay, so the observation is that this is observation 1 in this expression. Another observation is that given values for x, y, z, w, we can evaluate that m in polynomial. Okay, so this is Gaussian. Okay, or yeah, so whatever methods you guys have seen. Okay, so determinant of an n by n matrix can be found in actually time that's proportional, that's less than n cubed. So this is a standard norm. So now why did I talk about these? Right? So if I had a matrix M like this, what would be the determinant of this M? Okay, so in this very simple example, what would be the determinant of this M? I told you I have to sum over all the 6 permutations here, right? So you can try to see what happens for each one. Okay, so what if I pick 1, 2, 3? So I'm going to pick the first, I'll get an x, I'll get a 0, and I'll get a 0. Product of those is 0. Right? And if I pick 1, 3, 2, I would have got xwz. So I'll get xwz times the sine of 1, 3, 2. Plus what else? 3, 1, 2 again you can verify 0. In this case, you will be able to verify that every other permutation you pick, you will hit at least 1 0 in this matrix. Okay? And more generally, it turns out that this determinant for an arbitrary matrix, which comes out of a bipartite graph, is identically 0 if there is no perfect matching, and the perfect matchings always survive. Okay, so in this case, the reason 1, 3, 2 survived is because 1, 1, 2, 3, and 3, 2 was a perfect match. Okay, so this is the reason this term survived. Okay, because 1 matching to 1, 2 matching to 3, and 3 matching to 2 was a perfect match. Okay, so that's the only reason all these entries were non-zero in this matrix. Okay, so this turns out to be a general fact. So I won't prove it formally, but so fact, this actually, I guess from this picture now you should guess why this is Zm is 0, is identically 0 if M has no perfect matching. And it is not 0 if M has it. So if M has multiple perfect matchings, then this expression would be a mess, right? It would be a sum over all the perfect matchings of some weird polynomial. Okay, so it would be sum for a polynomial where the terms correspond to each perfect match. Okay. So this is what this thing is. Okay, but when it's not here, it doesn't matter what it is. Okay, so, and that's the whole point. Okay, so now your question of checking if a matrix has a perfect matching or not has boiled down to you have this matrix of some variables and you want to test if the determinant of this matrix is 0 or not. Now I just told you that if you plugged in values, the determinant can be computed efficiently in polynomial in n time. Now you just use this principle that we had earlier from identity testing, this is the Schwartz-Zipf lemma, and just say, okay, I just plug in random values for these xij values, okay, and I test if this determinant is equal to 0. And if G had a perfect matching, then with good probability this test is going to return a non-zero answer. So otherwise, you must have been unlucky and somehow you hit the roots of this polynomial. So this is a randomized test for checking if a graph has a perfect match. Okay. So this is and the test, as you can see, has nothing to do with the graph problem, right? You build a matrix where you have these variables, assign random numeric values to these xij's, compute the determinant of this matrix, and if it's non-zero, then you declare that it has a perfect matching. If it's zero, you try for a few times, and yeah.
For this method, don't you have to make n factorial calculation?
No, so this is what I was saying, right? So even though my expression for the determinant involved n factorial terms, yeah, this is a very good question. Okay? So even though my expression involved n factorial terms, there are other ways of computing the determinant that are much faster. Okay, and this is like Gaussian elimination and some of the things you might have seen in linear algebra course. Okay, so there are ways to compute the determinants in time that is much faster than n factorial, time less than n cubed. In fact, you should know that computing the determinant is almost equivalent to computing matrix products. So yeah.
So this doesn't give you what the actual matching is.
It does not give you, yeah. So this is another great point that I forgot to mention. Yeah, so this is a way of testing if a graph has a matching or not without actually giving you any clue of what the matching is. Okay?
Could you look at like the random numbers you chose and see what multiplications of those make for the matching, and then somehow match?
No, so the problem, so that would work if your graph had a unique matching. Okay, but if there were multiple matchings, then you would get sum over all these things. Okay? But of course, there's ways of doing these things. You can say, okay, I now have a procedure that can test, right? So now I say, okay, I forcibly include an edge, and I consider the rest of the graph, and I see if that has a recursive. That I test recursively if that has a perfect match. Okay.
So this is actually
No. You mean it's a polynomial time algorithm, right? So it's
I guess I'm asking like the problem of finding the perfect matching is that since there is a way, a problem of how to verify it is.
oh no. Okay, so this is very actually no, it's not NP complete. We'll get to that. Okay, so yeah, so all right. So I mean, in fact, you can find it. So I was just describing a procedure. So if you had an oracle that tells you if a graph had a perfect matching or not, you can actually use it to find the matching, because what you can do is try every edge, include it in the matching, remove these two vertices from the graph, check if the rest of the graph has a perfect matching. If yes, then okay, then declare that this edge was in the perfect matching and keep going. Otherwise, you try with a different edge. And this is a polynomial time algorithm, and this would recover the matching as long as you had an oracle. Okay, so yeah, usually even for NP-complete problems, if you had an oracle that that decides if for example, an instance of Boolean satisfiability is true or not, for those of you who know what I mean, you can actually construct an assignment. Okay, so we'll get to all those things later on in the course. Yeah.
So I was wondering, with the determinant thing equal to 0, if I understand the problem sort of correctly, can variables like x, y, z, w, can those be like any arbitrary real number, or are we assuming that they're either like 0 or 1?
No, they can be arbitrary real. Yeah. So in this example, this determinant as an expression is exactly equal to the sine of 132 times xwz. And the rest of the terms are 0. Yeah. In general, this will be a degree n polynomial involving these terms, and it would have one term corresponding to every perfect match. The rest of the terms will become 0. Okay, so this is, spend some time thinking about this, because this is a very beautiful result, and it connects a lot of things that you wouldn't ordinarily expect to be connected. Okay, so firstly, it has this component of having, of relating matchings to determinants. And then we are using this randomized testing to evaluate this determinant at random points, and we are using to find out if this determinant is identically 0 or not. Okay, so there's a bunch of things going on. So this is a nice, very nice application. Okay, and note that this is all building on this very simple toy example, right? Like the toy example, all of you just thought, okay, where do things like this arise? And then we said that when you are testing if polynomials are equal, these kind of settings naturally arise, because if they were unequal, then there are lots of places in which they are unequal. So this is, it's kind of like that toy problem where in some sense there were lots of zeros. Zeros are like the places where they were not equal. So, and then this is applied to this problem of Portland. Okay. Alright. So the last example I'd like to give is so it's what is called primality testing. So how many of you have heard of this problem? Many of you have heard. Good. Yeah. So it's you're given a number q and you want to test if it's prime or not. So and as usual in this case, like we had with like integer multiplication and so on, we assume that q has n digits. Q1, Q2, Qn. And your running time should be polynomial in n. Okay, so that's the whole. Okay, and assume that these qi's are binary. Okay, so you have a binary representation of this number. And right, and you want to test if this number is prime or not. Okay, you want poly n. Okay, so maybe I should have given more space for this problem. So yeah, so primarily testing. And this is an interesting question because I mean, if you had an n-digit number, can you test if this is prime or not in polynomial in n time? Because the standard test would be check up to square root of q, and square root of q is something like q is the standard test is check all the up to square root of q. D divides. So note that checking if D divides Q can be done very quickly. Okay, so it can be done in time which is polynomial in n. Do you guys all know why? Okay, yeah, so think about this. So testing if D divides Q can usually be done in time which is very fast. Okay, so this can be done in time. In general, if you have two two numbers, both having at most n digits, you can check if one divides the other in time, which is polynomial. So this you can verify. Yeah, so actually, this is the reason people actually like primality testing. I mean, that's why it's a very basic problem, because you can add, multiply, you can do division and stuff like this in polynomial in n time. Can you check primality in polynomial in n time? Yes, that's the reason we're interested in this. Okay, but this process, the square root q is complicated. Right? So square root of q is something like 2 to the n by 2. Okay, so if you have an n-digit number and you take its square root, it turns out it has something like n by 2 digits. So this in particular is not great. Okay, so this has running time which is 2 to the n by 2 times some polynomial. Okay, so this is exponential. Okay, so, but it turns out that if you allow randomness, there was actually a very simple algorithm. Okay, so so maybe a little bit about the history of this problem is that initially people realized that in the 60s, this is the test I'm going to talk a little bit about, that if you allow randomness, now randomized algorithms, then this can be done in poly n time. So this is actually an interesting number theoretic result. So I'm not going to prove it, I'm just going to tell you a gist of what the structure of this proof is. Okay, so this is an interesting, this is by, I think it's usually attributed to Miller and Rabin, but it existed before as well. So, yeah, so this can be done. And for a long time, people wondered if you can do this deterministically. Okay, like without the use of randomness, can you do this? And this problem was finally settled in something like 2002, I guess. This was a very famous paper by Agarwal, Shahil. Yeah, so it's done by two of the authors, family guys. So, and these guys showed that there is a deterministic polytime algorithm. Polytime. And now people know of running times in like n to the 6. Okay, so it's pretty fast polynomial time. So that's like a quick history of this problem. Yeah, there's a lot in between. So in fact, earlier also there were deterministic algorithms known assuming some math in there. So there were those that were known. But yeah, so the point is that this is a very basic question, which is non-trivial. Alright, and so what this Miller and Rabin test did was actually at its core very simple. Okay, so what it involved is a test that took a number between 1 and q, or 0 and q minus 1, and it did a certain number theoretic test on a and q. Okay, and this test would be done in polynomial in n time. And it has this nice property that if q is prime, then this test passes for all a less than q. And if q is not, then it fails for half the number. This involves finding what's called a non-trivial square root. Okay, so this is how this test works. And note that once you have this, you are essentially done, right? So then you're back into this toy problem of a being 0 at a bunch of numbers and 1 being and non-zero in half the number, right? Because if it is prime, you pass this test for all a. If not, it fails for at least half. So you just pick random numbers and do this test of a comma q. And if it was composite, then with good probability you will encounter one such number very quickly. So this is this is the priority test. So yeah, I'll include a link if you guys are interested on the discussion. Just post a discussion and include a link to this. Okay, but in general, you can look up Miller-Rabin test. All right, so let's stop.